Well, welcome everyone to seminar number 32, and today's topic is neutron stars. Exotic objects second only in their strangeness to black holes, and a topic which is an active field of research. So there are many things we don't know about neutron stars yet, but we'll find out. I can get the slide to work. Okay, so I'm going to quickly review some basic facts about the physics and quantum mechanics that we'll need to understand neutron stars. So almost everything in nature begins with a discussion of atoms, because the atoms control the properties of all these objects that we see around us. And so an atom is quite simple. It has just these three parts to it. It has a large cloud of electrons, which are negatively charged, that circle a very much smaller nucleus that contains two different types of particles. In general, protons and neutrons. The protons have a positive charge, and that's what attracts the electrons and keeps the atoms together. And the protons and the neutrons interact through the strong nuclear force, and they interact with the electron through the electromagnetic force. The masses of the proton and neutron are nearly the same. The neutron is slightly heavier, and they're both nearly 2,000 times more massive than the electron. And one of the most important parameters of nature is the difference between the mass of the proton and the neutron and its relationship to the electron. So a neutron has the mass of a proton plus about 2.5 times the mass of the electron. So a neutron can decay to a proton plus an electron plus a neutrino, but a proton in general cannot turn into a neutron because the neutron weighs more. If you want to turn a proton into a neutron, you have to add energy. It's what chemists would call an endothermic reaction. Electrons or protons seem to be completely stable particles. The experimental measurements are that the half-life of an electron is at least 10 to the 28 years. The half-life of a proton is at least 10 to the 32 years. And by comparison, the age of the universe is about 10 to the 11 years. So these are quantities that are vastly larger than the age of the universe. Neutrons, on the other hand, are sometimes stable and sometimes they decay. If they're in a nucleus, then they're typically stable, so they will last forever. But if you have a neutron in isolation from everything else, then it will decay with a half-life of about 10 minutes. And as I said before, it decays into a proton and an electron of opposite charge, and a neutrino that has no charge. Reactions like this in the particle physics world are completely reversible. So a proton, an electron, and a neutrino could combine and form a neutron. And if they were to do that, they would have to have sufficient energy to overcome the fact that the mass of the neutron is more than the mass of these particles. Now, a neutron star is the end stage of a star of quite substantial mass. So let's start with stars and see how we can end up with things like neutron stars at the end. So a star is a assembly of gas that has sufficient mass so that the force of gravity will squeeze its core until the core temperature reaches several millions of degrees, and that's sufficient to sustain the ultimate fire of nature, which is nuclear fusion. We'll discuss some more about nuclear fusion shortly. In order to do that, in order to sustain nuclear fusion, the mass of the star has to be significant. It has to be at least 8% of the mass of our sun. And the most massive stars that we see in the universe today are in the order of 150 times the mass of our sun. We believe that possibly the very first stars created at the beginning of the universe might have been as massive as 500 times the mass of our sun. But such stars don't exist anymore. And stars can be stable for billions of years, thus enabling life on nearby planets, due to an exquisite balance between two enormously destructive forces, and those are the core pressure and its own self-gravity. So the pressure in the center of a star, which is created by the energy released by nuclear fusion, seeks to blow the star into smithereens. And at the same time, the gravitational attraction of every piece of the star on every other piece of the star wants to crush the thing down to nothing. So you have these two destructive forces, and they can exist in this exquisite balance to parts per 10,000 for billions of years. And by doing so, the luminosity of the star is relatively constant for billions of years, and that makes it possible for life to evolve on a nearby planet like ours. Okay, so let's talk about why nuclear fusion is so remarkably special. If you have a normal chemical reaction, you have, for instance, an oxygen atom combining with two hydrogen atoms to make a molecule of water, then these light green clouds are the electron clouds, and the yellow circles in the center are supposed to represent nuclei. They are not nearly to scale. The nucleus is about 100,000 times smaller, but we wouldn't see it if I made it to scale. Well, when these atoms combine, they change the way they're sharing their electrons. And that's the basis of any chemical reaction. And in the process, some of the energy associated with the electrons in their orbits is converted from mass into energy and released as energy, and which is why we use this for rocket fuel, because a tremendous amount of energy is released, relatively speaking. But in fact, this is an extremely inefficient process because nature didn't put the energy of an atom into the electron cloud. Nature put the energy in the nucleus. And in any chemical reaction, the amount of mass of the original objects that's converted into usable energy is less than 1 part in a billion. So if you burn 1 billion tons of oxygen and hydrogen, you can only get the equivalent of 1 ton of energy being released. 1 ton of mass converted it, according to Einstein's equation, into energy. So you're left with a lot of stuff that you may or may not want. If you burn coal, you end up with a lot of toxic waste, greenhouse gases, and lots of terrible things. If we try to get the energy out of a nucleus instead, which, as I said, is where nature put the energy, then there are two approaches. One is you make the atoms smaller, and one is you make the atoms bigger. And making the atom smaller is called nuclear fission. You break the atom apart. If you take a very large atom like uranium and you break it into two still quite large atoms, a lot of energy is released. In fact, 100,000 times more energy is released per pound of fuel in a nuclear fission reaction than in any chemical reaction. So this makes it a much more powerful source of energy. The end products, however, are radioactive and troublesome. The alternative to that is you make bigger atoms out of smaller ones. And this is called nuclear fusion. This is what stars do during the normal course of their existence, throughout their entire existence until the instant in which they die. So nuclear fusion is putting these small atoms together to make bigger atoms. And I've illustrated here taking 4 hydrogen nuclei, fusing them together to make the nucleus of helium. You need to convert some of the protons, half the protons, into neutrons to do that. But so it's a multi-stage process, but from the beginning to the end, ignoring the intermediate steps, what you've done is taking 4 hydrogen nuclei and made 1 helium nucleus. And in the process, you've released 40 million times more energy per pound of fuel than a typical chemical reaction like burning coal. So 40 million times is an enormous factor. This becomes substantially efficient, and it has the additional attraction that it produces no radioactive waste, it produces no greenhouse gases, and in fact, what it produces as the end products, carbon, oxygen, nitrogen, iron, and all the elements in between, are elements that are essential to the existence of life. And all of these elements were produced in stars by the process of nuclear fusion. They are not produced in any other way in the history of the universe. So nuclear fusion is the process that makes the stars shine. It's the process that supports the energy necessary for life and produces the atoms that are necessary for life. So it's a unique and critical phenomenon in the universe. Now, as the stars age, they go through a series of steps. The least massive stars can only sustain the first step, hydrogen being fused to produce helium. The most massive stars can drive through a series of stages all the way to producing iron. And intermediate masses will produce some of these and not the rest. Each stage of this nuclear fusion process requires a more massive star that has a higher core temperature and pressure, and each fusion stage produces nuclei that are more and more massive until you get to iron. Iron being the tightest bound atom on the periodic table, there's nothing to gain by fusing it into larger nuclei. That would require energy input instead of energy output. Well, the larger, heavier nuclei naturally sink to the bottom of the gravitational potential well of a star, which is the center of the star. And so a star that is mature and has burned through all the steps of nuclear fusion will look like an onion. It will have the heaviest elements in the core, surrounded by shells of lighter and lighter elements. And finally, the outside will be the lightest element, which is hydrogen. If you take a star that has a mass of 25 times the mass of the sun, a very massive star, there are very few of those, you find out that it will burn hydrogen to produce helium, the first stage of nuclear fusion, at a core temperature of 100 million degrees. This is on the Kelvin scale. And it will do that for 7 million years. And after 7 million years, it has exhausted its hydrogen in its core. There's still hydrogen in the star, but it's not in the core and subject to the temperature that would sustain fusion. The next step would be for the star to fuse its helium to make carbon. That requires a higher temperature, 400 million degrees on the Kelvin scale. And that process will go very rapidly and will be completed in 500,000 years. So you've gone from 7 million to 500,000 in the next stage. And a following fusion stage would be carbon being fused with helium to produce oxygen. That requires a core temperature of 1.7 billion degrees, and all of that carbon will be consumed within 600 years. And finally, you fuse silicon to produce iron. That requires a temperature of 7 billion degrees in the core of the star, and all of that will be done in 1 day. So the fusion rate goes by the 4th power of the temperature. So as you get to these higher and higher temperatures, the process proceeds extremely rapidly. And as I said, the last one just lasts 24 hours. Well, what happens then? You've run out of every fuel that can be fused excuse me, to produce energy. And so you've exhausted the availability of the nuclear fuel inside the star, inside the core of the star in particular. And so the energy will stop being, new energy will stop being produced in the core of the star. The energy that has been produced already will dissipate outward and be radiated from the surface of the star. So the temperature in the core will drop, the pressure will drop, and now the pressure is no longer sufficient to combat gravity. So gravity that has for billions of years been struggling to squeeze all this gas down to nothing is finally going to win the battle over pressure, and it will compress the core more and more. And as the core gets smaller, the force of gravity increases with the square of that scale, and eventually it will catastrophically implode. So the core will collapse into something very small, which is the interesting part that we'll talk about next. And there will be so much energy released that it will blow the outside layers of the star off into space. So more energy will be released in a few seconds than the star has produced in its entire life that could have lasted billions of years. It's a catastrophic explosion. And the most dramatic of these are called supernova. And they can be brighter for a short period of time than an entire galaxy. So we think of a star as producing a tremendous amount of energy, and it does. But when the star comes to the end of its life, it produces an amount of energy that's spectacularly greater than everything it's done before. And this is an image of a star that's about to come to the very end of its life, blowing off its outer layers. And if this was a supernova, it would be destroying everything for trillions of miles. But at the same time, it would be seeding the cosmos with the atoms of life, with the carbon and the oxygen and the nitrogen and the iron and all the other elements that it has produced during its lifetime. So nature is recycling. So it turns out that this collapsed core can end up in only one of 3 different states. And so we'll talk about each of those. 95% of stars will have cores whose mass is less than 1.4 times the mass of our sun. That's the magic number. And they will become white dwarfs. So let's talk about white dwarfs for a second. You know, we discussed last week the property of these elementary particles that are the constituents of matter, the fermions, that all fermions are antisocial in the sense that 2 identical fermions will never share the same quantum state. And if you will, you could say that each fermion demands its own turf. It can share with non-identical fermions, but it never is willing to share with an identical particle. So electrons refuse to share their state with other electrons, protons with other protons, and so forth. And this is a reflection of the fact that these particles have wavelengths, And another reflection of that fact is the Heisenberg uncertainty principle. A particle that has a wavelength cannot be confined both in its position and its momentum. So there is a spread of position, which might be the horizontal width of this box. And there's a spread in the momentum, which is the vertical width of the box. And the uncertainty principle says that the product of those two, the height and the width, has to be bigger than some number. It's a constant of nature. We write it as Planck's constant divided by 4 pi. That's the best case. It could be worse than that. It would have to be bigger than that, but this is the smallest that it could possibly be. This is the least turf that a particle will demand. So if you take two quantities, multiply them together, you could think of that as being height and width in some abstract space. And this is an area then. So it's saying that within this space defined as the combination of momentum and distance, each particle demands a certain area, a certain turf. And it cannot be restricted to less than that, and it won't share with identical particles. So if you have a star, these particles are going to be, in the normal situation of a star at high temperature, these particles are going to be scattered throughout the volume of the star and throughout a whole series of different energies. And they take an enormous volume of this phase space. But when the star starts to compress, all of these particles get squeezed together, and eventually they come to the smallest total area that they could possibly have. So the electrons, let's talk about the electrons first because they have the biggest wavelengths. So they're the first problem to overcome. If you squeeze all the electrons together, they'll look like this. They're going to be completely abutting one another, taking up the least total volume of phase space that they can, but they will resist being compressed into anything smaller. In fact, they will refuse to be compressed into anything small. And this state in which all of these particles are compressed into their minimum total volume is called a degenerate Fermi gas, named after the physicist Enrico Fermi. Degenerate meaning it has the lowest state. So when you have a star and it starts to compress, you're going to squeeze all these particles together. And if you keep squeezing, gravity is squeezing it harder and harder, then you can reduce the width of the star only by increasing the energy of these particles. And so the particles are occupying the same amount of area, but now you're reducing the width and at the expense of increasing the height. So you have to add energy in order to squeeze those particles to higher energy states. And if the star is not too massive, so that gravity is not overwhelming, then this requirement to raise the particles to an ever higher energy state will eventually cause the star to stop collapsing further. And this is the state of a white dwarf. A white dwarf is the state in which the electrons are squeezed to the minimum volume that they will accept, and that there is no space between, no available phase space that's not occupied by electrons. Typically, what will happen for a star with a mass of about the sun, whose core has a mass of about the sun, is that the width of the star will be compressed by about a factor of 100. That's not a fixed number. It depends on the mass of the star and so forth, but that's a typical number. The star will become typically 100 times smaller than it was originally, and all of the electrons are now compressed into the minimum volume that they can have. So this is a picture of a white dwarf at the very center, and this array of colorful objects, colorful gas that's been expelled from the star used to be the outer layers of the star. So here you have an object which is more or less the mass of the sun, compressed into a ball that's more or less the size of the Earth. So the object is now millions of times more dense. There are three alternatives, as I said. Neutron star is the middle one. Let's skip over to the other extreme first. If the star is extremely massive and its core ends up being 3 times the mass of our sun or more, and there's only one out of every 1,000 stars that are massive enough for that to be the case, then the collapsed remnant will become a black hole. No force of nature can stop a star that massive that has such enormous gravity from collapsing down into basically nothing. This is a picture of a black hole that is fortunately nearly 1 billion light years away. The black hole is at the very center of this image. You can't see it directly. It's actually very black, but it's surrounded by material that's falling in. And as that material goes through the last throes of collapsing into the black hole, it's emitting radiation, which we see as infrared light in this case. So the black hole has a magnetic field, and charged particles that are falling in, a small fraction of those are ejected along, and they spiral outward along the magnetic field lines of the north and south pole of the black hole. And so you get these jets of charged particles moving at, it's estimated, 1/3 of the speed of light. And they are like giant flamethrowers blasting through the cosmos, destroying everything in their path. This object from one end to the opposite end is 5 times the size of our own galaxy. And all of that is created by a black hole that is 1 billion times the mass of our sun, but confined into a tiny ball, an invisible ball, that's 10 to the 20 times smaller than a single proton. So this is a phenomenally dense object, almost zero size, and yet incredibly massive. Well, so you have the white dwarfs on the one side, and you have the black holes on the other side. Many more white dwarfs than black holes, and the neutron stars are the middle case. So these are stars that are whose cores are somewhere between 1.4 and 3 times the mass of the sun. And so they are too massive for the electrons to stop the collapse, but they are not so massive that the neutrons can't stop the collapse. So let's see how that works. Now, the gravitational potential energy is a negative number because the gravitational potential energy is defined to be 0 for 2 objects that are infinitely far apart. So as the objects come closer and closer, then they have a larger and larger negative gravitational potential. As the radius decreases, the distance between the 2 particles decreases, energy is being continually released. And that energy release in a collapsing star is this immense number that drives a supernova that can be brighter than an entire galaxy. So there's plenty of energy being released. And so it's possible to combine the electrons and the protons with this extra energy into neutrons, which are heavier. That's why you need the extra energy, plus neutrinos. And so you have an atom that is 50 or 100,000 times larger than its nucleus. And if you squeeze out the electrons, then you're just left with the nucleus. And so you've allowed the object to collapse by this enormous factor. And if all of the atoms in the star do this, then you're just left with a single nucleus plus a fabulously large number of neutrinos that shoot off into the vast beyond and are gone forever. And that's what a neutron star is. So you have squeezed and squeezed and squeezed and got rid of the electrons, which are these big fluffy things, and you've condensed everything down to the most massive of the primary particles, which are the neutrons. So you've gotten rid of almost all the electrons and almost all the protons, and you've converted everything into a bunch of neutrons plus neutrinos that sail off into the sunset. And relative to a white dwarf, you are able thereby to further reduce the radius by a factor of about 500. So now, instead of being thousands of miles across, this object is tens of miles across. And if the mass of the star is not so great that gravity will overcome even these neutrons, if the gravity is great enough to crush the neutrons further, then you get a black hole. But if the mass of the star is not quite that great, then the neutrons can eventually cause enough resistive pressure to stop the collapse. So the neutron stars are at this delicate balance point. They are too heavy for the electron pressure to withstand the force of gravity, but not quite heavy enough for the neutron pressure to resist the force of gravity. So they live in this middle land between the white dwarfs and the neutron and the black holes. So we can talk about the spatial curvature here. This is the curvature factor that comes up in general relativity, 2m over r. These are in units in which Newton's constant is equal to 1 and the speed of light is equal to 1. And it's a measure of the strength of gravity. Earth on this scale is about just over 1 part per billion. The sun has a surface gravity of about 4 parts per million. A white dwarf is about 3 parts per 10,000. A neutron star is about 0.3, and a black hole is 1. At the event horizon of a black hole, 2m over r equals 1. And that's the maximum curvature that is mathematically possible. Okay, so what's going to happen to these exotic remnants, these white dwarfs, neutron stars, and black holes? Well, they, under certain circumstances, they can last forever. But they can also evolve if they're in a neighborhood with other things that they can interact with. So a black hole has a great deal of gravity, so it can suck in gas from its neighborhood, and it can also collide with and merge with other black holes or other neutron stars or even white dwarfs. And so the black holes can continue to grow without limit through these processes of accretions and mergers. And there are black holes that have been identified that are up to 60 billion times the mass of our sun. So they didn't start out that heavy. They've grown through these processes, and there's nothing that's stopping them from growing even further. However, if the black hole was isolated so that there was no gas to fall into it and nothing else to merge with, then it would eventually evaporate through the process that Stephen Hawking discovered or He didn't discover it in the sense that he detected it. He discovered it in the sense that he found a mathematical prediction for its existence. So this is called Hawking radiation, and it's a consequence of quantum mechanics. And it says that a black hole that, for instance, that has a mass of 6 times the mass of our sun will radiate a certain amount of low energy light, infrared light, and over the course of 1 trillion years, that black hole will radiate enough Hawking radiation so that it loses the mass of a single proton. So you take the mass of a proton, you multiply by c squared, you get a certain amount of energy, and that's the amount of energy a black hole will lose in 1 trillion years if it has a mass of 6 times the mass of the sun. This figure, 1 trillion years, increases with the square of the mass. So if you had 60 times the mass of the sun, then you multiply this number by 100. So this is a very long time, clearly, and it's only lost the mass of a single proton. So if in 1 trillion years, one extra hydrogen atom falls in, then you reset the clock because now you've got an extra proton mass. So it's nearly inconceivable that an object like this can exist in the real universe without accumulating at least one hydrogen atom in 1 trillion years. And if it does that, it will never evaporate. It will keep increasing its mass at a sufficient rate that it maintains its total mass, and its total mass never goes to 0. You have to completely isolate the black hole for Hawking radiation to be effective and eventually evaporate the black hole. If you had this 6 times the mass of the black hole, 6 times the mass of the sun in a black hole, and it was completely isolated, it would take a total of 10 to the 69 years to completely disappear. And this number increases with the cube of the mass. So if it was 60 times the mass of the sun, then you would have 10 to the 72 years. These are astronomical numbers, just to pick a word. And it's theoretically a wonderful idea, but from a practical point of view, it's unlikely that any black hole can be sufficiently isolated for this to be effective. So the bottom line is that black holes will continue to grow in mass through accretion and merger, basically indefinitely. White dwarfs and neutron stars can also grow by accretion and mergers. And if a white dwarf attains a mass that's bigger than 1.4 times the mass of the sun, then its electron degeneracy pressure will no longer sustain it, and it will explode in a type 1 supernova, and the remnant will become a neutron star. If a neutron star continues to accrete and merge and increase its mass, if it gets to something in excess of 3 times the mass of the sun, and we're not quite sure what that number is, it's more than 2 and probably less than 3. If it gets to that mass, then it will spontaneously collapse into a black hole. So these objects might exist forever if they're in isolation, but if they also are growing in mass, then they eventually will climb the ladder to more and more exotic outcomes. And the number 1.4 times the mass of the sun is called the Chandrasekhar limit. And it was the notion of the Indian physicist Subramanian Chandrasekhar that the electron degeneracy pressure could only sustain a maximum mass of 1.4 times the mass of the sun. So this is an artist's sketch of a white dwarf. which is accreting material stripping gas from a companion, a red giant star. And eventually the white dwarf will get massive enough that it will explode in a supernova type 1. This is an image of a supernova, the first one that occurred after the invention of the telescope that was in a nearby galaxy. And so it's a very popular object with astronomers. We saw the supernova in 1987, and it's an object, we think this supernova may have produced a neutron star as its final outcome, but we haven't been able to confirm that yet. The alternative would be that it produced a black hole. If you'd had a teaspoon of neutron star material, it would weigh 3 billion tons, and the gravity on the surface of the neutron star would be about 100 billion times Earth's gravity. So some key dates as far as neutron stars are concerned. The neutron as an elementary particle was first proposed in 1920 by Ernst Rutherford. The first neutron was actually discovered by James Chadwick in 1932. And in 1933, Walter Baade and Fritz Zwicky proposed that neutron stars could actually be composed entirely of neutrons, as we've discussed. And in 1967, the first neutron star, which was of a special type called the pulsar, was discovered by Jocelyn Bell Burnell and Anthony Hewish. And they were impressed by how regularly the repeating radio pulse from the pulsar was. As we'll discuss, they are wonderful clocks, tremendously stable oscillations. And the beep, 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 beep was so impressive to them that they called the first one LGM1, which they thought came from some alien intelligence, and LGM stands for Little Green Men. Something that is tangential to this, Fritz Zwicky is quoted as saying in 1948 that every one of us is potentially a genius, and our educational systems must allow each student to absorb whatever develops his own genius, lest he become frustrated. Clearly, we don't do that. Okay, so some other key dates in the discovery of neutron stars. In 1974, from 1974 to 2004, over a period of 30 years, Hulse and Taylor studied this so-called binary pulsar, 2 neutron stars in mutual orbit, one of which was a pulsar, and they plotted the change in the orbit of the neutron stars, the precession of the perihelion of the orbit, and it matched the predictions exactly of Einstein's theory of general relativity, which predicts gravitational waves. So the gravitational waves emitted by these 2 orbiting massive bodies gradually reduce their orbital energy, and this tracks exactly with the calculation that Einstein made. In 2017, we were actually able to detect the merger of 2 neutron stars for the first time by the Laser Interferometer Gravitational Wave Observatory, LIGO. And this is an image of the signal that was generated, and this is called a chirp. It starts out at a very low frequency, and then as the objects actually come in contact with each other, the frequency jumps very high at the end. So it's whee! The neutron star that was involved in this merger had an estimated mass of 2.14 times the mass of our sun. For many decades, it was believed that neutron stars had to have just about 1.4 times the mass of our sun, and we didn't know of any neutron stars that were more massive than that. But now that LIGO is searching for these things, we're finding more and more neutron stars that have larger and larger masses. So we don't know exactly how high that limit is. It's somewhere between 2 and 3, and we're creeping up toward 3. The pulsars are neutron stars that are rapidly spinning, that are emitting radio beacons. And the highest frequency neutron star, the one that's spinning the fastest, is rotating about itself 716 times every second. And that means the surface of the star is moving at about a quarter of the speed of light. So these are very, very exotic objects indeed. Theorists are grasping with what exactly is going on inside a neutron star. And so far, we've just talked about the fact that it's full of neutrons, and that was the theory for quite a while. One has to try to estimate exactly what that pressure is. And to do the calculation, you'd have to know more about the physics of nuclei than we actually do. And so this is a series of different theories, these curves. And the leading theory for a long period of time was the one in the light blue named APR. And it said that the radius of a neutron star would only be slightly more than 11 kilometers. And when the curve turns over, then that's where the neutron star would collapse into a black hole. So that would give a mass of like maximum mass of 2.1 or 2.2. Now we have some more data. These are measurements of pulsars by the NASA satellite X-ray observatory called NICER, N-I-C-E-R. And this gives an estimate for the radius and mass of this pulsar. We have measurements from the gravitational wave observatory for the collapse of these two neutron stars. That gives us some other data. So we have a few data points now, only 4 or 5 or so. I mean, it's still very early days for this science. And we have pushed the mass limit up beyond what was typically thought as the maximum value, 1.4. And so now theorists are struggling to figure out how could something have that large a mass without collapsing into a black hole. So one way is you start making new particles. So if you have a lot of energy being released from the collapse of the star, so energy is not there's tons of energy available to create other things. So electrons can convert into a muon, which is about 200 times heavier than an electron, plus 2 neutrinos. And the muon is more massive, so you have to supply a substantial amount of energy. And if you do that, then the electron, then you no longer have, you convert one of the electrons into a different fermion. So you take a particle off the top of the stack and you create a new stack with a new color. And it no longer has a conflict needing to share phase space because it's a non-identical fermion. So that reduces the pressure. You can also take a neutron and add energy and get what are called hyperons. So these are other composite particles. A neutron is a composite particle of 3 quarks. These are also composite particles of 3 quarks. and you would have a pion in addition to this in order to conserve the electric charge. And so again, you create a new color on the phase space that's no longer in conflict. So you take a particle off the top of the stack and stick it on the bottom. And if you pursued this to its limit, you discover that you've reduced the pressure in the center of the neutron star by a huge amount, and it would therefore collapse into a black hole. So this can't happen without some limitations. If this happened to the maximum extent that these reactions are allowed to proceed, then the maximum mass of a neutron star would be much lower than we know they are. So there has to be something beyond what we know now that limits this process. This is a different paper. This paper was published. This paper was published yesterday. This paper was published in November of this year, and it's an attempt to calculate how the different types of particles in a neutron star exist in different portions of the star. So in the center of the star, the density is the highest, and you end up with a lot of these hyperons and muons and less neutrons. And this is one attempt to do the calculation. This is another paper, and it says that when the density gets to be very high in the center, then all these protons, neutrons, protons and neutrons disappear, and the quarks that are inside them come out. So the quarks are deconfined is the word, and you end up with equal amounts of up quarks, down quarks, and strange quarks. So up quark has a charge of +2/3. The down and the strange have a charge of -1/3. And if you have equal numbers of all of them, then the star is electrically neutral, as it must be. So maybe this is what it is, and maybe it's something different. So we have probably in excess of 100 different theories that try to explain this, and we don't have enough data to eliminate the theories that are wrong. If you then take a cross-section of what a neutron star might look like, the very outside would be like the surface of any other star. It's a plasma consisting of ionized atoms and electrons, mostly ionized hydrogen. So the protons and electrons would be the dominant composition. And that would only be about 100 meters thick or less.
No, I just want you to attend to it.
Excuse me. Then you would have maybe a kilometer worth of the typical neutron star that we talked about. Below that, at higher density, you would have something that is called a neutron pasta. So this is some sort of superfluid version of neutrons. The neutrons would create the equivalent of the Cooper pairs of a semiconductor, and that would allow them to act like bosons. So they are no longer fighting for their individual turf. Bosons are social gregarious particles, and you would have this mixture of individual neutrons acting as fermions and this neutron pasta acting as bosons. And in the very highest density area in the core, you would have these deconfined quarks, the up, the down, and the strange quarks. So maybe that's right, maybe not. Just one more. We have this shows the data points better. We have this limitation established by the gravitational wave observation of the merger of two neutron stars. We have 3 pulsar, this is another gravitational wave measurement. This one is particularly intriguing because the calculation of the gravitational wave merger is that a black hole merged with something that has a mass of 2.6 times the mass of the sun. So that something is either the heaviest neutron star ever observed, or it's the lightest black hole ever observed. It's right in the boundary zone between where we think neutron stars end and black holes begin. So that is, it has a very large uncertainty in its radius. So we don't know much about the radius, but, and these 2 are pulsars measured by the NICER telescope. And the curves are theoretical attempts to rationalize the data. But there isn't much data. We're going to have more data in the future, and that's going to help the theorists converge to what we hope is the right answer. Another interesting paper, which was from September of this year, is from the Indian Institute of Science in Kolkata. And they make the statement that all these other theorists have done the calculation as if space-time was flat in a neutron star. And indeed, we know that the curved space-time around a neutron star is second only to that around a black hole. So it's the greatest curved space-time in the universe except for black holes, and you ought to do the calculation in a fully general relativistic fashion with curved space-time. And so this is their calculation if you do it in flat space-time, and this is the calculation if you do it in curved space-time, and that gets you to a maximum mass that's very close to 3. So the curve says that as you increase the mass, the radius gets bigger and bigger and bigger, and at some point, it the pressure of the elementary particles isn't enough to withstand the force of gravity, and the object will collapse. Okay, this is we talked about the discovering neutron stars because we observed these radio beacons, which are from what we call pulsars. These are neutron stars that have a very strong magnetic field, about 1 billion times the magnetic field of the Earth, and they're rapidly rotating. We said earlier that the highest rotation rate yet observed was about 716 complete spins per second. And so you have a object that's rotating about this vertical axis, the red axis, but it can have a magnetic field which is pointed in a different direction as Earth does. This one is quite askew. Earth's is not nearly that tilted. And the particles, the radio beams are coming off from electrons spiraling around the magnetic field. And so the radio beam is in the direction of the rotational axis in each direction. And it sweeps across the sky as the pulsar rotates around its rotational axis. So if we're lucky, it sweeps past the direction of Earth, and we pick up a radio pulse, beep, 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 many times per second. And because it has such a high mass and therefore such a high moment of inertia, the rotation rate is extremely stable. So they make wonderful clocks. There's a supersized version of pulsars called magnetars. These are probably very young pulsars. They have magnetic fields that can be 1,000 times more than a pulsar. 1,000 trillion times the magnetic field of the Earth. They are proposed as one possible source for these fast radio bursts that have been discovered, for which we're searching for a why. And if you had a very massive star, 10 to 25 times the mass of our sun, that goes through a supernova, it's possible that it could create a neutron star with a magnetic field as high as that, and this would be the origin of magnetars. It is proposed, and they would slowly run down. The rotation rate would slowly decrease, the magnetic field would slowly decrease, and over thousands of years, maybe 10,000 years, they would fall into the class of a normal pulsar. So the magnetars are infant pulsars, if you will. And the association with fast radio bursts is that we have seen in at least 2 situations that a fast radio burst came from the same direction in the cosmos as we have identified the existence of a magnetar. And this paper that's referenced at the bottom, which was from this month of December, estimates the magnetic field. So this is 28,000 trillion times the Earth's the Earth's magnetic field. And they estimate that this comes from a supernova that occurred only 14 billion years ago. There's a supernova remnant in that vicinity, the magnetar in the middle, and they can estimate the age of the supernova remnant by how far it spread. So the estimate is it's only 14 years old, very young for astronomical objects. This one similarly is 22 years old. The age comes again from the size of the supernova remnant, and you know, they're on the order of 500 fast radio bursts that have been detected, and 2 of them have been identified as coming from magnetars. So maybe they all are, or maybe that's just one of many different ways that fast radio bursts can occur. It's all cutting edge science, so we don't have the answers yet. And this is one of the neutron star mergers that's in fact the first one and the most famous. It was the merger of 2 neutron stars that had masses of 1.5 and 1.3 times the mass of the sun. They were in orbit around each other. They collided, and eventually, because they radiated their orbital energy away in gravitational waves, which is why we detected it. And after the merger, we believe that the resulting object collapsed into a black hole, and it produced an explosion of optical light, which is called a kilonova. So this is the gravitational wave analysis, the waveform with the chirp. And 1.7 seconds later, 2 satellites in Earth orbit detected gamma rays, a gamma ray burst from the same direction in the sky. And so this was the kilonova explosion. And the timing and the location are similar enough that virtually everyone is convinced that it must be the same event. And so we have captured the whole process of 2 neutron stars colliding to form a kilonova explosion and a black hole. And after the signal was received of this gamma ray burst and the gravitational wave detection, every available telescope on Earth and in orbit around Earth slewed over to that direction of the sky to gather as much information as possible. And within 24 hours, 80 telescopes had made observations of that event, and 100 research papers were submitted within 24 hours of the event, authored by a total of 4,000 astrophysicists, which is about 1/3 of the total number that are alive today. So it was the greatest feeding frenzy in the history of astronomy. This was the gravitational, the gamma ray burst that was associated with the merger. And we were able to see this kilonova light up in the sky. This is a Hubble Space Telescope image over several days. It was, brightest, and then it's gradually dimming. And it's because we see where it is in the sky and what galaxy it's associated with, we can measure the distance to it. And we have a measurement of 130 million light years, which is quite close on the scale of the universe. And because the gamma rays arrived 1.7 seconds after the gravitational waves, we don't know that they're produced at exactly the same time, but if you assume that they are, then you can compare the two velocities of the gamma ray velocity with the gravitational wave velocity, and that proves that the gravitational waves are moving at the speed of light, the same speed as the gamma rays, to 1 part in 10 to the 15, which is a very fine confirmation of Einstein's predictions. So the kilonovas are something between a supernova and a nova. A nova is a new star. It's typically the creation of a white dwarf, and it releases a certain amount of energy. A kilonova releases about 1,000 times more energy, hence the kilonova, the name kilo. And that is about 1% of the energy released by a supernova, which is the explosion of a much more massive star. So a supernova is 100 times, 1,000 times more energy release than a nova. And it's estimated that the number of kilonovas is probably a few hundredths of the numbers of supernovas in the sky. So this, a star exploding in a supernova is probably 50 or so times more probable than 2 neutron stars merging. So you need two things to collide with one another, which is less likely than one thing just coming to the end of its life. The kilonovas are identified as being possibly the major source of all of the elements on the periodic table that are heavier than iron. So iron is most tightly bound nucleus on the periodic table. And if you want to make a nucleus that's heavier than iron, then you have to supply energy to fuse smaller atoms to make something heavier than iron. And the energy that you require comes from the explosion of the star, or the merger of the 2 neutron stars in this case. And it's estimated that this particular kilonova produced 16,000 times the mass of the Earth. Yeah, the total weight of the elements that it produced, heavier than iron, would be equivalent to 16,000 times the mass of the Earth. So that's an enormous quantity of these heavy elements. And the The kilonova that we are referring to was discovered in 2017, hence the code. And looking back on historical images, they think they may have detected in optical telescopes such events occurring in the past. They hadn't been properly identified at the time, but looking back at the data, there's evidence that we may have detected these 3 previous events before we realized what they actually were. And lastly, an amusing PhD thesis from a gentleman from the University of Southampton discusses mountains on neutron stars. So is it possible for some collection of matter to stick up over the surface of a neutron star? I think we mentioned earlier that the gravity on the surface of a neutron star is 100 billion times Earth's gravity, so it's hard for anything to stick up. But if they were accumulations of mass for whatever reason that did stick up, then this gentleman analyzed the gravitational waves that they would produce, and he estimates that the mountains could be as tall as 1/3 of a millimeter. Not exactly what we call mountains, but 1/100th of an inch. So this is sort of the ultimate case of trying to make mountains out of molehills, I guess. But if they were, they would produce special gravitational waves. Okay. So we'll have time for questions, but I wanted to update you on what the future seminars hold. January, we're going to talk about neutrinos. The first seminar in January, on the 4th of January, we'll cover the physics and the theory of neutrinos. And neutrinos are different from everything else. Everything about a neutrino is different from everything else. So we're back to square one, trying to figure out what's happening with these particles. And on January 18th, we'll talk about some of the more important experiments that are being or have been done to examine all these exotic properties of neutrinos. And in particular, it was requested by one of you, and I'm happy to include a discussion of the experiment that's called IceCube, which is located at the South Pole. And it uses the Earth as an absorber. So it looks for neutrinos coming up from the ground. Neutrinos produced on the opposite side of the planet that have passed through the planet. Earth is big enough to block everything else, and but not neutrinos. So neutrinos stream out, and if you're lucky, one of them interacts in the detector. So IceCube is the world's biggest ice cube, I guess. It's 1 kilometer on a side. So you have a cubic kilometer of ice at the South Pole, and that ice is under so much pressure from the ice that's above it. There's about 1.4 kilometers of ice above it. And that makes the ice nearly transparent, as it turns out. And so we have drilled holes and fitted out photo detectors, and we look for flashes of light in this ice cube at the South Pole. It's really fun stuff. Okay, so that's what's coming. And then we have 2 more seminars in this series number 6, and they're scheduled for February 1 and the 15th. There are a number of topics that we could discuss, and I will send out an email for you guys to vote. We can talk about gravitational wave observatories of the future. That's something that people have requested. And also telescopes of, more conventional telescopes of the future, and all sorts of other things as well. So let me know what excites you, and if I can figure it out, we'll talk about it. Okay, so are there any questions about neutron stars?
Robert,
Yes, Jill.
you know, when neutron stars collide, how does the gravity, how is the gravity affected between creating gravitational waves and making the collision possible? I would assume there's just a certain amount of gravity, but is a lot lost in gravitational waves?
So how much of the energy of the objects is lost by gravitational waves?
Yes.
Yeah. Almost all of the motion energy that the neutron stars originally had is lost to the gravitational waves throughout the process of them coming together, throughout the process of their separation getting smaller and smaller and smaller. And most of it is lost in the last burst. So if you remember that chirp,
Yes.
the chirp picture,
Yeah.
it's a very sharp, it's a very sharp peak.
It's a great sound too.
Yeah, it's a very sharp peak at the instant of merger. So almost all of the energy from the well, no, let me take that back. It's exactly one half. One half of the energy of motion of the objects originally is eliminated, is transferred to the gravitational waves and eliminated from the orbits. And the other half of the energy that's released goes into an increased velocity of the two bodies. And that energy feeds the creation of the remnant, which would be the black hole, plus it feeds the energy released in all of the visible and all of the forms of light. So the optical, the visible light, the infrared, the ultraviolet, the gamma rays, X-rays, and everything else that gets eliminated in the explosion of the supernova. So it's half the energy has to be removed from the orbital motion, and half the energy is transferred to a higher velocity of the objects.
So it's a big gravitational release or exchange when this merger happens?
Yeah, so if you have something fall into a black hole, for example, half of its total mass energy can be released by the decrease in gravitational potential energy. Half of its mass is released during the infall process, which is an enormous quantity. If you burn coal, 1 part in 10 billion of the mass energy is converted into the heat from burning coal. 1 in 10 billion. For a black hole, it's half. So it's what, 5 billion times more? I mean, imagine you're burning coal and all of a sudden you get 5 billion times more energy than you expected and burn the house down, right? It incinerates you. So this is an energy release on a scale that we have no direct experience with. I mean, it's a phenomenal release of energy.
Wow. Thank you.
Yep. Any other
Robert?
questions? Yeah.
According to what you said, then we don't expect to find any black holes smaller than several times the size of our sun.
Well, yes and no. As far as we know, all the black holes were produced by the death of stars. So they would have to,
Except those that were produced at the Big Bang.
except there may have been black holes produced earlier than stars. Not at the Big Bang, but stars came into existence 2 to 4 to 600 million years after the Big Bang. The very first stars were about 200 million years after the Big Bang. And it's possible that after we know enough about the evolution of the cosmos up to, let's say, 300 seconds after the Big Bang, to know that normal matter did not participate I'm getting tongue-tied here. We know enough about the evolution of the universe to realize that the amount of matter that we see in the universe today is consistent with the amount of matter that existed 300 seconds after the Big Bang. So black holes could have been created early on. They could have been created after the formation of the light elements, but before the first stars. And probably they can't be created directly after that. After the first stars came, the density of matter in the universe was probably insufficient for gas to collapse directly to make a black hole. But gas could have collapsed directly to make black holes at earlier times. It's theoretically possible. And there are a whole bunch of experiments that say it didn't happen. And they have set limits on how much material could have collapsed into black holes of different mass ranges. And there are something like 20 different experiments that preclude substantial numbers of primordial black holes at different mass intervals. Not 100% of the intervals are covered. So there are 4 intervals of mass. Hang on a second. There are 4 intervals of mass that are still open windows in which there might have been formed a significant number of black holes of those masses. And it's a very intense debate among theorists as to whether that's actually happened or not. There are some theorists who say that there is enough of this, there are enough windows at the right masses that if black holes formed in those masses, they could account for as much as 100% of all the dark matter in the universe. And there are other theorists who say that's complete nonsense, which is normal. That's the life of a theorist, right? So you're guessing about things for which there isn't evidence. If there was evidence, we wouldn't be guessing. So people are searching for more evidence to try to identify whether or not these so-called primordial black holes really do exist or not. If they were super light, they would have evaporated by Hawking radiation, so that eliminates that group. And if they're super heavy, we would find them by gravitational lensing experiments, which we don't. So there's a mass
What's the
range of,
smallest one that would not have evaporated?
what is the mass of the smallest one?
That would not yet have evaporated by Hawking radiation.
About the mass about equivalent to an asteroid. It's 10 to the 15 grams.
So if there are any small black holes, then they have to be at least the size of an asteroid, and they came from early in the universe. There's no other way to create them now.
There would be, we know of no other way to create them now. They would, the only way we can imagine them being created was when the density of matter was very high. And the argument is whether or not there were areas that were more concentrated enough to collapse into black holes. So the question is, how much are the deviations from the average density? And that's the key of the strong debate. Did I answer your question?
Absolutely, very good answer.
No, thank you. My wife accuses me of filibustering and not answering questions.
I think we're good at answering questions.
Okay, anybody else have a question? Okay, so we're going to talk about neutrinos, and then we've got room for 2 more topics in this series. And frankly, I'm coming to the short end of my list. So, another topic was other beautiful experiments. And some of you had ideas about what you thought were beautiful experiments. So if you want to help me come up with a game plan on that, that would be good too. Okay, thank you all for being here today, and I'll see you in January. Have a happy holidays.